All right. Uh, we're trying something new for this recitation. We're doing like APMA style. We wrote up these notes, and we were going to print them off, but then we just kind of ran out of time. Would that have been helpful if we had printed off these notes so that you guys could fill them out as you go, or would that not have been useful? We'll upload them after we finish filling them out. But okay, cool.
So we're just going to go over first the partition function of Quicksort, and then the full algorithm for Quicksort. And then a bit later we'll get to the K-select and your nth place loser, which is relevant for your homework. And yeah, as Max said, we'll put these up after we're filling them out online on Colab.
Yeah, we'll post them on Colab.
Alright, so partition array, or partition function. We're starting with this array here. We have our low index, we have our high index. The goal here is we're starting at so that we have 0, 1, 2, 3. So we have this part of the array, 4, 5, 6, 7, 8, 9, 10. So our subarray that we're going to partition is 5, 2, 3, 8, 7, 3, 4, 5. Right? What?
Is that a 5 there?
Yeah, my handwriting may be a little messy. Let me know if you can't read anything.
Yeah, we're trying this out for the first time.
Yeah.
Tablets are hard to write on.
Okay. And so easiest thing to do here is pick your pivot to be just the first element, which is what we're going to do. So 5 is going to be your pivot. So you can kind of leave that on the side. And then we're going to have the rest of our array 2, 3, 8, 7, 3, 4. Why is it so much darker? Never mind.
Oh, the harder you press, the darker it is. Yeah.
So this is our array here. We're going to let I equal here and j equal here. So going through these steps here, we've done this. So low is our pivot. That's our 5 here. Let I equals low plus 1. So low was the 5, which is index 3. I is low plus 1. That's the 2 right here. So we've done that. J equals high right here. We've done that. So now what we're going to do is we're going to increment I all the way over until we find a value where the index is greater than 5. So what that looks like is so we start at I. We have 2. 2 is less than 5, so that's fine. So we bump I up to 3. 3 is less than 5, that's fine. So we move I up to here. Now we get 8. So we stop here for now because we've incremented until the index or the value at index I is greater than the pivot. We have 8 is greater than 5.
Any questions about that step there? We're incrementing I until the value at I is greater than the pivot.
So we have our pivot 5 here. 2 was less than 5, so we moved I over here. 3 was less than 5, so we moved I here. 8 greater than 5, so we stop. Right? So that was this step right here. Everybody clear on that? Okay. Now we're going to do a similar thing with J, except we want to see the element at index J. The stopping condition is when element at index J is less than the pivot. So 5 less than 5, nope. We're going to move J down. Decrement, because we're going to the left now. 4. Is 4 less than 5? Yes, it is. So we stop here. And now we have index I is 8. Index J is 4. Just rewrite this. 2, 3, 8, 7, 3, 4, 5. So we have I here. And we have J here. The next step in our function is to swap I and J. So we can just do that. So 4 and 8. So these two values are now, they're not in their proper positions yet, but so 4 is, what would you say? Like, never mind. So once we've done that, we come back up to here, or well, I guess we go to this step, repeat until I and j cross. So I and j are not the same yet. So we're just going to go back up to the top, repeat until I and j cross, back up here.
Well, no.
Oh.
Oh, we should have been more clear. Repeat back to the increment step.
Yeah.
You don't have to set the pivot.
No. You don't need to reset the pivot. So we go back up to here. So we're back to incrementing I along this way. After we do that, we're decrementing j here so we can find the middle pivot. That's like the end goal of the partition step, finding the spot to put our pivot P, our pivot 5. So we swapped 4 and 8. Should I be erasing or no? If we want them for slides later?
Probably not.
Okay. We'll leave these here. So these were just swapped into their new positions. Having 2, 3, 4, 7, 3, 8, and 5. I is right here. J is right here. So what we're going to do, we're going to increment I until the element at index I is greater than the pivot. So is 4 greater than the pivot? No, we moved it. We just swapped it there, so that's okay. Now we're going to move I up to here instead. 7 is greater than the pivot. So right here we stop. And now we go to this step. Decrement J down to here. 3 is less than 5, so this condition is satisfied again. So we stop. What do we do when we stop? We swap the elements. 2, 3, 4, 3, and 7. So these two just got swapped here. 8 and 5. Yep. So that is I, J. Any questions up to here? Okay. Yep, and so we're back here. We're going to repeat again, increment I until the array, the element at index I is greater than the pivot. But as soon as we increment here, we increment I to here, we see I and J are the same, which is this, which satisfies this condition, repeat until I and J cross. So right now, I and J are crossed here at this index, which is, so this was 3, 4, 5, 6, 7, 8. So this is 8 here. So right now we have I equals J equals 8 at this point here. So we repeat until I and J cross, they crossed at 8. So now last step, swap the pivot with I or J. Because right now I and J are the same value because we go until they're the same. So then you swap your pivot P here with your I or J.
Well, here you'd actually want to swap it with 3. So
Oh. Wait, how'd that happen?
basically, eventually I and J, they come closer and closer together, and eventually they're going to cross or be the same. And at that point, you want to swap the pivot into the middle of your array. But you have to be careful to swap with the lesser element. So sometimes I and J might not actually point to the lesser element. So there's a bit of a corner case there. But if you look at the code in the slides, it handles that corner case. So we just whipped up this pseudocode. We didn't really pay attention to that.
But you hit that corner case before you get I equals J, right?
Yeah,
You
I think
check when
so.
they're
Yeah.
adjacent. All right.
Yeah, I think the way it actually works is instead of checking if I and J cross, you check if they're 1 apart.
Yeah.
So if they're
let's go back
yeah.
to that, just to make that clear.
Yeah. So at the step where we swap 7 and 3, then we check if I and J are 1 apart, and they are.
So we can erase this entire array actually. So yeah, back up to this step, we have I was 7 because 7 was the next value greater than 5, going this way, and the value at J is 3 because J is the first value smaller than 5, looking this way. And so here it says repeat until I and J cross. I and J cross essentially means I equals J, or I minus J equals 1. So they're either at the same position or they're adjacent. And so if they're adjacent, what we're going to do is we need to look at the values, or no, so we still swap them, right?
Yeah, we still swap them, but then we just don't increment or we don't repeat anymore.
So we have 3, 7 now, just swapped, I and J. And so now we see I and J are adjacent to each other. So this is the kind of corner case where we need to take a look at the values. So in this case, if we swapped 5 with the 7, what would that look like? Well, we would have 7, our final array.
We would have 7 in the
Can I
front.
move stuff around
Yeah.
on the screen?
Yeah, if you hit the scissors, you can also shrink it too.
Oh God. This is. There we go.
Nice.
Okay. Okay, so now we're going over here. So, say we swapped the 7 and the 5, right? Because we're not really sure which one we want to swap, so we're just going to try the 7 and the 5. Our sorted array, or the partitioned array, would be 2, 3, 4, 3. Actually, there would be a. We're including the element, or this element now, because it's the final array.
What would be 7?
So this would be 7 first. 4, 3, 5, 8, 5, right? That's not sorted because we have a 7 here, a 2 here. So that didn't work out, right? So we're going to take a step back. What went wrong? Well, we swapped with the wrong value. Instead of swapping the 5 and the 7, we want to swap the 5 and the 3. And now, what would that give us? That would give us 3, 2, 4, 5, 7, 8, 5, right?
You can tell just by looking at that array that we've gotten closer to being sorted.
Yeah. So yeah, you're going to look at this and say, wait, that's still not sorted, right? Obviously. But the point of partition isn't to sort the whole thing. The point of partition is that, so we go back up to here, we had 3 was our low element, or the element at index 3 was this 5 here, right? In this array, 5 is sorted, right? So if you look here, everything on the left of 5 is less than the 5. Everything on the right of 5 is greater than the 5, right? So that is the idea behind the partition step. You pick an element. In this case, the element that we picked was 5, our pivot. And you put it in its correct place. And what that means is exactly that. Everything on the left of it is less, everything on the right than it is greater. Okay? Is that clear? Anybody have any questions about pivot? You feel comfortable that you could do a similar example? Yep. All right. Sorry, not pivot, partition. So partition is one of the key components of the Quicksort algorithm. Here we can look at the Quicksort pseudocode. The first step is partition, right? So this is our entire array that we want to quicksort. The first thing that we do is partition it into a subarray here, your pivot element, and then another subarray here. And then, well, actually, we're just picking the first element as a pivot,
Yeah.
right? So picking a pivot there are many different ways to do it. An easy way that works well most of the time is you just pick the first element, which is what we're going to do here. It's simple, it works pretty well, and it's easy. So we're going to call it's the same exact like partition function as above. And we're selecting our pivot to be 6. So you're going to have your 6, 9, 1, 3, 5, 3, 8, 7, 3, 4, 5, 8, right? So instead of going through and doing that whole partition thing again, since you guys feel comfortable with it, we can just say partition this. It's going to look something like this. So we can take all of the elements smaller than our pivot here. So that'd be 1, 3, 5, 3, 3, 4, 5, and that will be our left partition. And we have 6, and then we have the remaining numbers 9, 8, 7, 8. Right. Everybody clear how I got from here to here? Right. We picked the partition of 6. We pulled this, or 6 is already at the beginning. We called the partition function on this array, and just skipping all of the actual doing the partition, this is something that it would look like. 6 is in its sorted position. Everything here is less than the 6. Everything here is greater than the 6. Right? So that's the first partition step that we just did. Now we have these two steps. These are the recursive parts of the algorithm, so the recursive quicksort. So now what we're going to do, what does it say? Quicksort up to pivot. These here are the elements up to the pivot. So we're just going to call quicksort. That's not cute. Quicksort on 1, 3, 5, 3, 3, 4, 5, which is this array, right? And then what that's going to do is the same thing. We're going to pick 1 as our partition element. So we're going to have 1. And because everything in this array is less than 1, the partition of this is going to be 1 and then 3, 5, 3, 3, 4, 5, right? So it essentially doesn't change because we picked our partition as the lowest element. This is like the worst case of quicksort, is if you always pick the lowest element, because then every time you recurse, you're not splitting your array into 2 halves, you're splitting it into like 1 less than the size that it was. But for this, it's okay. And so now we're recursively still, so the left subarray is empty, so if we quicksort up to the pivot, that's just done. We're going to quicksort after the pivot now, so we're going to call quicksort on this. Pick your pivot 3. This is also going to be very similar. You just have 3, 5, 3, 3, 4, 5. This is an implementation choice for you, but so when you're going through the partition step, you have, well, 5 is obviously going to be on this side, but 3 is not greater than 3, so does it go on the right? It's not less than 3, so does it go on the left? Point is, it doesn't really matter. It's going to work out either way you do it, as long as you stay consistent and do it the same way. So for this, let's just say we'll put them all on the right side. So then that's that, and we have 3, 5, 3. That's weird, 3. All right. Should we step all the way through it? That might take a while.
Yeah, probably not.
Yeah.
The idea is that we recurse on both sides, though. So here we've been recursing on the left side. We partitioned the whole array. We've got a left and a right side on either side of 6. And then we started recursing on the left. And you can see every time we recurse, we're getting slightly more sorted. The only problem is when we recursed on the left, our pivot ended up being 1, which wasn't very helpful. But if we continued doing this, we would eventually get down to a sorted left. But then we would also have to sort the right side. So everything to the right of the 6 will also recurse on.
So this would branch down into a quicksort, and this would quicksort, and then just keep going. But then eventually it would just come back up and return. We would have what? 1, 3, 3, 3, 4, 5, 5. And then 6, 9, 8, 7, 8. So the recursive quicksort on this half of the function would go down, recursively quicksort, come up, and then return into this sorted first half of the array. And then we call quicksort on this half of the array. It goes down, recursively does quicksort, returns back up, and then we'll get our 1, 3, 3, 3, 4, 5, 5, 6, and then this would be sorted after the quicksort went through, and be 7, 8, 8, 9. Piece that all together, we have 1, 3, 3, 3, 4, 5, 5, 6, 7, 8, 8, 9, which is sorted.
So how much did you guys talk about the properties of sorting algorithms? Like, did you prove the runtime for Quicksort? Okay. Well, so Quicksort ends up being n log n on average. But like we saw here, when we picked 1 as the pivot, that didn't work out too well. And so one thing to be aware of is if you're doing Quicksort, let's say we're sorting this array, 1, 2, 3, 4, 5, 6. First step is to pivot the whole thing. We would pick 1 as the pivot. And so if we partition on 1, we don't do any work, right? All we do is leave 1 here. There's nothing on the right side. And then the left side is everything else. And partition takes linear time. So we just did a linear time operation and actually didn't do anything. So you can imagine now we would recurse on the right side and do another linear time operation. So you can maybe already see this would be quadratic because we're doing linear runtime operations, and each time we're only doing a constant amount of work. So we'd have to do a linear number of them. So we'd have to do a linear number of linear operations, so that's quadratic. So just keep that in mind. Quicksort is on average n log n. The catch is that there's a way to prove that it's there's a way to force it to be n log n, and there's a way to prove that it's almost always n log n. So we basically don't worry about it. But I guess if he hasn't proved the runtime, then don't worry too much about that.
It's so popular because the chance that you actually hit the n squared and that you pick your pivot on the first or the smallest or the largest element every time is so small that it's almost always going to be a lot better than n squared.
Yeah, the reason we got n squared here was because we took in a sorted array and we picked the first element as the pivot every time. So the way to counteract that would be to either shuffle the array first so that we know we're not taking in a sorted array, or pick a random pivot instead of the first element. So just things to note. Yep. Okay, any questions about Quicksort before we move on? Okay, k-select. So k-select, the algorithm basically takes in an array and a k and searches for the kth smallest thing in that array. So when k is 0, what does k-select actually do? So k-select, it takes in an array and then finds the kth smallest element. Yeah. So if k is 0, this is basically a min function. And if k is n minus 1, it's basically a max. And then if k is n over 2, then this is basically median. So that's just one way I like to think about k-select is we're finding these statistics about the array, either the smallest, the largest, the middle, anything in between. We can set k to be 2. Then we would find not the smallest, not the min, but the third to smallest. So that's the idea with k-select. So let's actually talk about how we could do it. One option would be to sort the array that we're taking in. So if we sorted this array, what would we get? We would get 1, 3, 3, 3, what, 4,
That's a sorted one.
5,
Above it.
oh, it's 5, 6, I'll pass. 6, 7, 8, 9, something like that, I don't know. Either way, we get a sorted array. If we were to sort the array, we would get something sorted. And then how would we find the, let's say, second K2, the K smallest thing. Yeah, just index the array. So if K was 0, we're finding the smallest thing, and if we just sorted our array, we just index at 0. So this is a really easy implementation for K-select. You just sort and index at K. The problem is that we know that the worst sorting algorithm is n log n. So that's an n log n way to find the kth smallest element. What did I say?
Worst.
Oh, the best sorting algorithm is n log n, not the worst. The worst is infinite, I
Doesn't
guess.
sort.
Yeah. So we have a better option. Our better option is to not fully sort the array, basically. Here we did all this extra work. If you think back to Quicksort, what did we do to sort this array? We chose a pivot, we kind of split the array in half, and then we recursed on both halves. That's a lot of extra work considering we're only looking for one element. Since we're only looking for one element, we don't really have to recurse on both halves. We can only recurse on the half we care about. So what we're going to do is kind of partially sort the array towards our goal. So let's just do it. Here we've got K-select on this array here. K is 3, so we're looking for the 4th smallest element because it's 0 indexed. So just like Quicksort, our first step is to partition the whole array. So we let 6 be the pivot, and so let's do it. If we were to partition this now, we would get 1, 3, 3, I'm sorry, 5, 1, 3, 5, 3, 3, 4, 5, 6, 9, 8, 7, 8. Does everybody see what I did there? That's how you partition just really fast in your head. You pick your pivot, and then you just go through the array once and pick out everything that's less than your pivot. Go through the array again, pick out everything that's greater than your pivot. And that's how you partition really fast. So we've got our partitioned array now. We've partitioned on 6. And what are we looking for? We're looking for the kth smallest thing. The 4th smallest thing because 0 indexed. What did we do here when we partitioned? One nice property of partition is that whatever your pivot is, you can be guaranteed that it's going to be at the correct index in the sorted array. So if we had sorted this whole array, we could guarantee that 6 would end up here. And that's just a property of partition. So what can we do? Well, we're looking for the kth smallest thing, 3. We can check the index of the pivot after partitioning. So what is this index? It's 0, 1, 2, 3, 4, 5, 6, 7. So the index of our pivot was 7. But we're looking for the 3rd smallest thing. So we know that the thing that we're looking for is less than 6. So we know it's on this half. Does that make sense? Okay? So if we know that it's on this half, we can just recurse on this half, and we can leave this half alone. We know for a fact that since we're looking for element 3 in the sorted array, we know where element 7 is in the sorted array, so we don't have to look anywhere greater than element 7. All right, so we recurse on this half. 1 is the pivot. So again, we do very little work. 1, 3, 5, 3, 3, 4, 5. 1 was our pivot. And so what's the index of our pivot? 0. 0 is less than 3. So we know that the element that we're looking for is to the right of our pivot. So we throw away the left half. It didn't exist. And we recurse only on the right. You see how we're kind of honing in on the element 3 of the sorted array without actually sorting the array? I think this algorithm is very similar to binary search. Because in binary search, you split a sorted array in half and search on one half. Here, we're splitting an unsorted array in half by partitioning it. And then we can recurse on one half. So it's very similar. So, okay, we're here at this array now. Our pivot is 3. So if we partition this, again, we don't do very much work. We end up getting 3, 3, 3, 5, 4, 5. So let's say that our pivot ended up, this was our pivot. We made a choice to put, if the 3's are equal, we put them before the pivot. So our pivot ended up here. What's the index of our pivot? 2. Any other thoughts? The index of the pivot is actually 3, because you can't forget that we're in the context of a greater array here. So that's index 0, that's index 1, that's index 2, that's index 3. So the index of our pivot was 3.
Wait, hold on.
You see? Mm-hmm.
Like, so we started and then we threw out half of our array, basically.
Yeah.
Like up there.
Yeah.
And then we come down and then, so even if we're not working on that array, it's still part of it. So like at that point I can index to like 8 and it would still be valid.
It would be valid. You wouldn't do it.
It would be stupid.
Yeah, you wouldn't do it, but you could do it. Yeah, so I'm kind of obfuscating what we're really doing here. When I say we throw away that half of the array, we don't literally throw it away. We just stop looking at it. But you still have to count those indexes. You know, it's not like here we eliminated 1, right? We knew that the kth smallest thing had to be greater than 1. But we still count its index because it's still part of the array. If we didn't count that index, then we would find the kth smallest thing of some random subarray, you know.
Or the kth smallest would always be 0.
Or yeah, I'm not quite sure what would happen. It turns out that implementation-wise, it's actually easier to do this anyway because you don't want to be copying the array every recursion. Yeah, good question. Okay, so the index of our pivot here just happened to be 3. And that's what k was. And remember that when you partition, we can be guaranteed that the thing that we pivoted on is going to be in its final position in the sorted array. So what we've done here is we've found the position of the kth smallest thing in the sorted array without actually sorting the array. So now all we have to do to get the element is index there. So we say array sub 3. And because we've partially sorted the array all the way down to the element that we care about, this access will return 3, which is the correct answer. The third smallest thing in this array was that right there. So you see we got the effect of sorting the array, but without actually sorting. So this turns out to be n instead of n log n. But I guess if you haven't talked about the master theorem, then you don't have to worry about how to prove that. That'll be the write-up. Any questions about quick select? Okay. So finally, nth place loser. You'll notice I didn't put pseudocode up because it's the assignment. But I hope that you'll notice some similarities to covered algorithms. And I hope that you'll look at the slides. So let's just go through this example, and then I think we'll call it. So in this example, we're looking for the third, n is 3. We're looking for the nth place loser. What that means is that we're looking for the nth largest element. So without sorting this array, let's just try to figure out what the answer is. The largest element is 9. Second largest, so this is n equals 0. N equals 1 is the second largest, which would be one of these 8s. So we'll say that's n equals 1. That's n equals 2. N equals 3 is going to be now the next largest thing, which is that 7 right there. So the answer is 7. How you implement this is up to you. That's the assignment. But again, my advice is to notice similarities to covered algorithms and to study the slides. Any other questions about nth place loser? I know I didn't really do much there for you, but I hope that other parts of the recitation will be helpful. Any general questions about the homework? Open floor?
Can you explain briefly why the runtime of Quicksort is so low?
Yeah, totally. So, let's see. So we're talking about the runtime of QuickSelect. I told you it's O of n. That's actually kind of surprising, because if you think about it, what we're doing here is, remember, partition is a linear operation, and we're recursing each time, and each time we recurse on 1/2. So you might be able to tell, just like binary search, we're going to recurse log n times, because we're recursing on 1/2 each time. So just like binary search, we're going to end up recursing log n times. And remember, I said partition is n. So you might think that this algorithm is actually n log n. But it's not. And the reason is that basically, when I said partition takes n, it takes n with respect to the amount of array that we're looking at. And the amount of array that we're looking at decreases by 1/2 each time. So in this specific scenario, the log n shrinks fast enough to where we don't have to count n in it. So it would be more like, the actual runtime would look something more like this. N plus log n. But of course, log n is big O of n itself, and so this whole thing is an element of big O of n.
It's backwards.
Yeah, backwards element of. You've never seen that?
I don't like that.
That's a backwards element of. Because it turns out O, big O, a lot of people write equals when they talk about big O. That's false. Big O, if you say big O of a function, big O of
Big
f
O is a
of
set.
n, that is a set of all the functions that grow equal to or less than the function. So because it's a set, technically it's more correct to use set notation here than it is to use equals. So that's why I wrote a backwards element of. If you add log n and n, the n dominates the log n, and so it just all ends up being big O of n. And you'll learn how to prove that. That's just an intuitive explanation. The proof is less interesting, actually. The proof is more of it's more just math. You can do the math and actually say that you can find a function for which this is asymptotically less than, and that function is linear. So, yeah. Okay, any questions? Did you guys hear about the revised bonus problem policy? No? Okay, cool. For some reason, Graham wants it to be on the DL, but hey, I figure this is DL enough. So, the bonus problems at first, the idea was that if you solve all of the regular homework problems and all of the bonus problems, you get an extra 50% added to your final grade. So if you were at a 65, you would then be at 115. We're sweetening the deal a little bit and saying that you can also use the bonus problems to make up for any missed homeworks. So if you missed LRU or something, or you're just not feeling it some week, you can do a bonus problem, and that'll take the place of a homework you missed. And you can even take the place of homeworks that you haven't missed. So if you, let's say you do every homework and one bonus problem, then you would get a 21 out of 20 on homeworks. So there's the extra mile bonus that'll basically guarantee an A. But then there's also the bonus of just doing a single bonus problem and it adding to your homework grade. So who's started looking at the bonus problems? Anybody?
Are they due by the end of the semester?
Yep. I think last day of class, something like that.
Do you guys offer insight, or is it because it's bonus?
We'll offer some help, but it's going to be limited. For example, like some people were
No
asking on
recitations
Piazza.
about
Hmm?
No
Oh
re-
yeah, there's not going to be recitations about them. So if you want help, you'll have to go to office hours. But one thing to note is that we signed the bonus problem, so you know who wrote which. So if you're working on Andrew's bonus problems, I would go to Andrew's office hours because I'm not going to know anything about it. And then the other thing is, oh yeah, so like an example of help that we're not going to give is for most of these homework problems, you'll know what runtime to shoot for. That won't necessarily be the case on the bonus problems. So that actually makes it a lot harder. But that's how it is in the real world. It's not like your manager will be like, come up with an algorithm, and I know for a fact you can do it in linear time, so that's what you should shoot for. You never actually know. So, for example, Rohit gives a runtime, but on my bonus problem, no runtime. I still know what the best runtime is, and so you'll still have to beat it, but I'm just not going to tell it to you. So that's support that I'm not going to give. But I'll help on other things, though. So. Okay, cool.